Okay, right. So acoustic levitation and volumetric displays is what I'm going to talk about. And I have a feeling that you came across this topic because of your reading of the great Physics World magazine, the magazine of the Institute of Physics, which featured a beautiful picture on the front there from a paper that we wrote recently where we created a volumetric display. So I'm going to talk about, first of all, acoustic levitation, and then that's going to flow into these things, well, using acoustic levitation to make volumetric displays. So I'm an acoustician, I suppose. I'm somewhere really between a physicist and an engineer, sort of working at that boundary between the two. And a lot of my work involves something very much like this, but not quite like this. Let me just get a laser pointer. Can you see that laser pointer there moving about?
Yeah, we can see that.
Take that as a yes. Okay, so I have some kind of sound source. In that case, looks like a CD player. I have an amplifier, and then I have some loudspeakers outputting sound, although in my case, it tends to be ultrasound. And basically, if you turn up the volume loud enough, sound starts to have a physical effect on objects. So if you've ever stood next to a very loud sound source or even a very loud musical instrument, you might have felt almost like an internal shaking and vibration of your body. Well, that wasn't an illusion, that was a real effect. And of course, an explosion, the thing that does all the damage is a shock wave, which is basically a type of sound wave. So essentially, if you have a hi-fi, you turn it up loud enough, you start to be able to move things around. We tend to do the experiments in the ultrasonic range, so above the range that you can hear, because the experiments would be too unpleasant to do, really, if you did them in the acoustic or the audible range. So that's but they would still work in the audible range if you wanted to do these kinds of experiments in the audible range. So my version of that, well, there's many different incarnations of it, but the one we did first, I guess, was this thing called TinyLev. So if you Google TinyLev, you can see it's been used for all sorts of different things. That's it in the middle, levitating a whole series of water droplets there. In the middle, you can get a kind of sensor scale that sits on your tabletop like that. And that there in that little black box are all the bits there. There's an Arduino, which is our signal generator. We tend to just generate simple sine waves, so a single frequency, usually 40 kilohertz. Then there's an amplifier box and an amplifier circuit, and then a power supply, and that's it. And they're being fed to these little black things there, which are my equivalents of loudspeakers. I tend to call them transducers, but they're basically ultrasonic loudspeakers. And there's lots of them because each one of them contributes a little bit to the sound field. And when you put together a whole load of them, you can get some really very loud sounds. Loud in terms of pressure, but not loud in terms of what you can hear, because it's inaudible. It's ultrasound at 40 kilohertz. So, you know, bats would be disturbed by this, but humans, no human could possibly hear 40 kilohertz. You can, if you're got good hearing, you can maybe hear up to 20 kilohertz. A few people can go maybe 22, 23 kilohertz, but 40 kilohertz is well beyond what you can hear. And on the right hand side, you can see this is a picture, if you could see it, what the sound field would look like. We create a standing wave. So this pattern, an interference pattern, basically. So of high intensity sound regions, they're the yellow-white regions. And then there's a kind of like a pattern of high intensity, low intensity. The black bits are low intensity, so it goes high, low, high, low. And the particles are shown superimposed on there. They sit at the low intensity regions, the so-called nodes. There's no displacement or no pressure in this case. And either side of them is a high intensity region. So a way you can sort of think about this is the particle is trapped there. If it tries to move in any direction, it gets pushed back down by this high intensity sound. I mean, the bit that's hard to get into your head if you've not seen this before is this idea simply that sound is carrying momentum with it, so it can push things. But seeing is always believing, I suppose, and this is online, so you can't really see it physically. You'll have to just believe that these things are not CGI. So here is a more complex version of that. So on the left-hand side are a number of objects, 6 objects being levitated in a device, and you can, if you look at the top, you can see that's made of many transducers, actually hundreds of these little loudspeaker things. On the right-hand side, you can see again it's a simulation, but it's what the sound field would look like if you could see it, and the particles superimposed. In order to generate that, what we do is we change the phase of these sine waves. So that at the top and bottom, you can see those multicolored things. That's not just for beauty. I don't think it's particularly beautiful. I suppose beauty is in the eye of the beholder, isn't it? But it's the colors represent the phase. So that's the timing of these sine waves, and so that phase creates that pressure distribution, which we've designed. I'm not going to go into exactly how we do that, but we say we want to trap these particles. We know what sort of field we want, what sort of pressure field we want, and then we do a calculation to work out what phases we have to apply to these transducers to generate that interference pattern. If you look at it, it kind of makes a bit of sense, because around each of the particles is one of those standing wave patterns that you saw in the previous one that is reasonably possible to understand, I think. So that's the more complicated one. Here, I don't know whether this is showing. Videos is never great across these things, but this is a video of a whole load of particles being moved together, and we called the device that did this a holographic acoustic tweezer. All these things need a good name. And there it is again. Is the video coming through okay? I'll take that as a yes.
Yeah.
Yeah, great. Okay. With these things, you can also grab bigger objects. So that's grabbing many objects. This is grabbing bigger objects. In particular, we want to grab them and keep them still for all sorts of reasons, observation and analysis being one of them. And so there we sculpt the acoustic field to match the object. Big, again, is in the eye of the beholder. So big here is a few millimeters. So you can see the length scale there, 3 millimeters, the typical size of these objects are all in the same scale. But I should have uploaded the videos, but if you see the videos, they're the boringest videos you've ever seen, because these objects just sit there doing nothing because the thing works. This is, right, yes, this is now trying to levitate really big things, really big for us. Again, is not necessarily things of human scale, but this is the last thing there that's just going in is a sphere of about 20 millimeters in diameter. You can see we're having to use quite a lot of these loudspeakers to do that. Then if you put small things in them, you can get these quite cool planetary effects, which is a kind of an offshoot of the nature of the acoustic field that we create in that particular case, which in that case is a vortex-like field. So now here is the super high-level version of what's going on here. So we've got our duck, which is the particle, and then we've got the wave in the bottom. And this is now, you can imagine this as water waves. They also carry momentum. If you ever, I'm sure you've been to the beach and you've stood in the waves and you've had waves crashing against you, they have a tendency to knock you down if you're not too careful, because they carry momentum with them. But here, the duck is out in the middle of the ocean, and there aren't breaking waves. There are just they could be big, but they're just the normal ocean waves. And there's no, in this thought experiment here, there's no ocean currents either, just waves. So under those circumstances, if the duck drops into the ocean, the duck just bobs up and down. Actually, the motion of a small particle of water on the surface in the mid-ocean is just a circulating pattern, no particular motion one way or another. So that wouldn't be particularly good to meet our objectives. What we've got in these systems is something much more like this, that it's like the breaking waves on the beach. So in order to get these effects, we've had to turn up the sound levels to a sufficient degree that they start to have a form like breaking waves, water waves. Just of course they're sound waves, you can't see them. And that basically means going to the point where the system is behaving non-linearly. It's a non-linear phenomenon, which is, you might appreciate, quite hard mathematically. In this circumstance, it's pretty obvious what would happen. The duck surfs the wave, surfing the acoustic wave. So that would be the duck getting, okay, he goes off one side of the screen and comes out the other, but he'd get pushed in a particular direction wherever the beam was sending them. So what do we need to do levitation and keep objects fixed in space is a little bit different. We want to create something like this, So this is again the conceptual map of what I have in my head. There's the particle, the duck, whichever direction it tries to go in. These springs, you've got to imagine they're grounded to something, but they're compressed and they push back. And in our case, it's the sound field that's doing the pushing back bit. But the critical bit is to trap and levitate an object. You have to have an acoustic field, in our case, that will push things back in all directions. So whichever way the duck tries to go, the particle tries to go, it gets pushed back. So it's a convergent force field. The lines of force are converging on the duck and it can't escape. And that's completely critical thing to achieve. And so when I said earlier we try to design acoustic fields, we're trying to design these acoustic fields by interference of these acoustic waves to create this converging force field. And then when you do that in a one-dimensional system, you have basically waves from both sides. The duck's trapped there, and by moving the point at which they meet, we could move the duck backwards and forwards. So if you accept that simple description, is a form of tractor beam. So it's not in this case an optical tractor beam like you might have seen in films like Star Trek and Star Wars, but it's an acoustic tractor beam in that we can apply force at a distance and we can push and pull objects by adjusting this acoustic field pattern. But 3D displays are not real, or are they? So there are plenty of people that have postulated 3D displays, so some kind of physical thing that could exist. You can wear glasses that will give you a 3D effect, but that isn't a true 3D display. Here I'm meaning a display that you could walk around and observe from different angles and it would appear to be real. So, but then actually there's a way into this. So this is our way into this. So if you get a sparkler or whatever they're using here and wave it around, due to this effect called the persistence of vision, you are left with the impression that sparkler was everywhere, or at least you could write your name or whatever you like with it, and there's the sense, or your brain perceives it as being there, but it isn't. So the idea is, can we do something like this with acoustics? So we were thinking about this some years ago, and had a PhD student working on this kind of topic, and then out of the blue came this paper, which was an optical version of this, what they call a photophoretic trap volumetric display. Phoretic is just a kind of a fancy word for force. And they created some beautiful graphics, as shown on the right-hand side, where they had trapped a very small particle with an optical beam, and then moved it around very fast and created these. I say very fast. The pictures at the bottom right were taking about 20 seconds to form. So not quite a true display, but making huge progress towards a true display. And things like that Y shape, which I think is the emblem of their university, perhaps, can't remember now. But anyway, whatever it was, that was done in more or less real time. So if you observed this thing, you would see that Y there, and you could, in principle, walk around it and observe it, and it would appear to be physically there. But there's a big but here. They used a pretty powerful laser to do this, and in fact, it's a class 4 laser, so it would blind you. So the terrible consequence here is that you have a 3D display that would destroy your eyesight should you choose to use it. So you can take pictures of it. I mean, you could observe it perhaps really carefully from the right angle and it wouldn't destroy your eyesight, but it doesn't sound like it's the holy grail of 3D displays. So we were still in business, and we could carry on our project trying to work out an acoustic version of that, which we think would be safer, and potentially it could enable the display to be bigger. So what does it look like? Well, shown there is our levitator device. You've got to imagine there's an array of little loudspeakers, top and bottom there. We create the acoustic force field, trap a particle, and by adjusting the phases really quickly, we can move this particle around. And whilst we're doing that, we shine basically a projector at it, which we can change its color. So as shown on the right-hand side there, the particle moves around in a circle. So it's moving because it's trapped in this acoustic field, and we're changing the phases to move it around in a circle. And then we're shining different colored light at it, so its color appears to change as it moves. And we wrote this up in a paper, and that was the thing that was shown in that Physics World article. They wrote a little article about our paper. Pretty much simultaneously, or a few months later, was another paper. So there was another group, another UK group actually, that also created a volumetric display on the same principle. So they're essentially more or less, well, in 2019 anyway, there were two papers. We were there first. We were there in July. They were there in November. But it'd be fair to say their display is a little bit better than ours. Have a look at them on the internet if you like. But I'm going to talk about our one, and the basic physics of them is exactly the same. Yeah, you've got to do some careful calibration. So there's the circle we're trying to create. If you use an open loop control system, you get a distorted version. But if you do careful calibration, you can get the particle to do what you want. Obviously, that's pretty important. What's it look like physically? Well, there's a photograph of it. There are the loudspeakers, top and bottom. There's the particle. And here's the camera that we're viewing this through. And you can see it's illuminated. So we shine a pretty bright light at the particle so that it appears very clear. And then we can create these graphics that you saw right at the beginning on the front of Physics World. So we can create these simple shapes in the order of about a second. We can create these more complex shapes in the order of about 5 seconds. And we can do raster graphics, well, depending on how big a raster graphics you'd like to do, in the order of 20 seconds. So basically, our capability was really exactly the same as the optical trapping device. The other group from University of Sussex that published a paper on this a bit after us have got a bigger system that works a bit faster, and so they've upped the speed from this by about a factor of 10, which is quite critical because at 1 second exposure time, that's not enough to fool yourself, to fool people that it's really a 3D effect. You need a refresh rate to be of the order of 1/10 of a second to start fooling the eye and the brain that it's a physical object there. So we didn't quite achieve that. It's now been achieved in acoustics by another group, so that's good. That proves the basic principle. What we did more recently was we took a step back and tried to work out what is the theoretical limits of these kind of devices. So what could you do in principle? And so this is a graph out of that piece of work there. I'll try and quickly explain what we've got here. We've got density of the object along the bottom. We've got the size of the object on the y-axis, and then we've got the size of the display in this color bar here. So this is in millimeters. So at the top there, anything that's that yellow is a 180 millimeter display. So we could millimeter thing at 10 hertz. So basically, if you can tune into these regions here, these yellowish regions, you could in principle get a display. So this is kind of a map of where you might take it. Obviously, going lower density and larger has its problems. What limits you is below this purple line. It's the drag of the air that limits you, and to the right hand side, it's the inertia of the particle that limits you. Anyway, there's a map which suggests that an acoustic display, if someone wanted to have another go at this, you could really get quite a big one that would work in real time. So that's quite cool. In parallel with that, we've also done other things, not necessarily displays, but things like using these acoustic forces to move cells around. So this is a simple standing wave system where we use the waves to align cells into columns. This is some collaborative work with some people at Imperial College. We line these, so it's like the acoustics is positioning the particles into the cells into a particular pattern, and they then grow into muscle fibers. So that's just a slightly different use of this same kind of technology at a much different scale. So here we're using megahertz, so millions of cycles per second, and wavelengths well below a millimeter to do these kind of activities. Just to kind of finish off, you can do a calculation as to what might be possible for these sorts of things. So if you have some mass here that you'd like to manipulate, this is a bit of having a think about how big an object you might want to, or you could in principle move. So there's an incident wave field, a reflected wave field, and the combination of those two means you apply a force. In order to levitate something, you've got to beat gravity. So the first one tells you, you don't bother need to read them. I'll tell you the answer in a minute, but just get the basic idea here. That the first one tells you the force that the acoustic wave applies. That's like the momentum that you've transferred to the object. This one here is the gravity that you've got to beat in order to levitate it. If you equate those and rearrange it, you basically get this P, this amount of acoustic pressure. This is like the volume on your dial that you have to apply in order to levitate things. And if you look at this equation here, you've got a load of constants that you can do pretty much nothing about. And then you've got the mass of the object. So the heavier the object is, the more pressure you have to apply, the louder the sound. And then you've got area. So the bigger the object, the more sound it's kind of like catching. So it's like a bit like a sound umbrella. So the bigger your umbrella, the lower the pressure you need to do that. So the ultimate thing to be levitated is, I guess, a light and flat, large object. Here are some things you might want to levitate, and there's a history in physics of trying to levitate frogs. You'd need 160 decibels, which is just about possible, and this level of sound, which is on the outer limits of what's possible. So this back of the envelope calculation tells you that it might be possible to levitate frogs with sound should you want to. What happens to the frog is another story. Here are some other things. Jumping straight to this one here, there's various conspiracy type stories on the internet which suggest that the pyramids were built by aliens, and they did that using acoustic levitation. I'm not sure I'm a believer in, or I'm sure I'm not a believer in that approach, but if you can use that back of the envelope calculation to have a think about that. So you needed to generate 187 decibels, which is huge. That's like a major explosion. And you need approximately 10 megawatts of power, of acoustic power. So because the loudspeakers are not particularly efficient, you'd probably need tens, if not hundreds of megawatts of power to levitate one stone. And then you'd obviously have to think what to do with it once you'd levitated it. Well, the physics says that if you could achieve those things, then you could do it. But achieving those things is not something that we have the current technology to do. But perhaps the aliens have got there first, as ever. Right. Thank you very much for listening to that. That's all I have to say.
So thanks Bruce for your talk. It was really interesting. So we're a bit short on time, so we'll only have time for one quick question. If someone in the audience has one. Nope. Okay. Well, thank you very much for coming and taking the time out of your day to speak to us. It was really exciting. So if everyone else wants to join me in giving our speaker a round of applause.